So what was the equation for electric potential again? Electric potential is given by 1 by 4 pi epsilon 0 into Q over R. This is the equation for electric potential. What is the definition of electric potential? Work done to bring a plus 1 coulomb from infinity up to the concerned point. So if we have a charge here plus Q, and if there is a field around it, this is called a field, right? I can draw a boundary like this, and that will be called a field, electric field. Just like a magnet has a magnetic field, a body has a gravitational field, a charge has an electric field, electrostatic field. Okay. And I told you this is a boundary beyond which there is no influence of electric field existing. Okay. Electric field exists only inside the boundary, in between, I mean, within the boundary only. And then if you want to find the potential here, potential at a distance r, you can use this equation 1 by 4 pi epsilon 0 into Q upon R. And this is actually what? The work done. Work done for what? Bringing what? Plus 1 coulomb. From where? From infinity. Up to which point? Up to the concerned point. So if you want to bring something to this point, you must do this much of work. Okay, and that is known as potential 1 by 4 pi epsilon 0 into Q by R. Okay, now what is potential energy? I'll tell you something about potential energy now. This is potential equation for potential. Okay, right. See this. I have a charged particle here. This is Q1, right? And I'm bringing a charge plus 1 coulomb here. What is the work done for it? The work done is 1 by 4 pi epsilon 0 into Q1 over R. Right. So if I bring a charge of Q1 coulomb, if I bring plus 1 coulomb here, the work done is 1 by 4 pi epsilon 0 into Q1 divided by R. What if I bring 2 coulombs? Into 2. What if I bring 3 coulombs? Into 3. If it is 4 coulombs? Into 4. If it is Q2 coulombs, 1 by 4 pi epsilon 0 into Q1 by R into Q2. And this work, so instead of plus 1, I am bringing what? Q2. And this work is stored as potential energy inside the system for this system of particles. Okay, I'll explain that one more time. What did I have? I'll start off from the beginning. Right. So I take a charge. I take an independent charge. Look at this. I take an independent charge here. This is an independent charge Q1, which creates its own field. Okay. And if I want to bring a plus 1 coulomb here at a distance of R, the work done is called what? The work done is called potential 1 by 4 pi epsilon 0 into Q1 over R. This is the potential at the point. Okay. So potential is actually what? This is the 4th time I'm telling you today. Work done to bring a plus 1 coulomb from infinity up to the concerned point. So in order to bring plus 1 coulomb, you must do this much of work. So if you want to bring 2 coulombs into 2, this much into 2. If it is 3 coulomb, this much into 3. 4 coulombs into 4. 5 coulombs into 5. So what if you're bringing Q2 coulombs? 1 by 4 pi epsilon 0 Q1 by R into Q2. So this is what? This is the work done. Work done for what? Bringing Q2 coulombs instead of 1 coulomb. Right. And this is called the potential energy of the system 1 by 4 pi epsilon 0 Q1 Q2 over R. This is called the potential energy of a system of two particles. Potential energy is actually defined for a system only. You can't define a potential energy of a single particle, isolated particle. Potential energy is meaningful only if you got more than 2 or more particles. Understood? So I got 2 particles here. The potential energy is 1 by 4 pi epsilon 0 Q1 Q2 by R. What is this? Work done for what? Bringing what? Q2 coulombs where into the field of Q1. So I'll illustrate the situation. I had a field here Q1. I had a field here Q2 of Q2. They were actually infinitely separated. Look at this. Boundary of the first one is not intercepting with that of the second one, but you are bringing them closer such that they are merging into a single field Q1 and Q2. Now this is exactly what happened. Understood? So work done to assemble the charges to their present separation from their infinite separation is known as potential energy. 1 by 4 pi epsilon 0 Q1 Q2 by R. This is for a two particle system. If it is a three particle system like this, Q1 Q2 Q3, look at this, Q1 Q2 Q3, where the distance between 1 and 2 is R12, distance between 2 and 3 is R23, distance between 1 and 3 is R13. In such a case, the potential energy is given by 1 by 4 pi epsilon 0. That is common. Then you have to take them in the cyclic order, right? What is cyclic order? 1, 2, Q1, Q2 by R12 plus Q2, Q3 by R23 plus Q1, Q3 divided by R13. That is how you find the potential energy of a three particle system. And there is n particle system also, but that is not there in your syllabus. It's a JE question, okay? I'll quickly explain it one more time. Look at this. What are we looking at now? This is called potential energy of a system of charges. We have seen potential, we have seen potential difference, equipotential surfaces. Now it is the turn of potential energy. Potential energy is what? Potential energy is the work done to bring Q2 coulombs into the field of Q1 coulomb. Okay, so I'm writing the first equation, right? This is what I had only Q1 here. The work done to bring a plus 1 coulomb is 1 by 4 pi epsilon 0 Q1 by R. And if you're bringing Q2 coulombs instead of 1, it is 1 by 4 pi epsilon 0 Q1 by R into Q2. So that makes it 1 by 4 pi epsilon 0 Q1 Q2 over R. This is the potential energy of a two particle system. If you extend this to a three particle system, look at this, 1, 2, 3. R12, between 1 and 2 it is R12, between 2 and 3 it is 2R23, between 1 and 3 it is R13. So I can write the potential energy for the system here, 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. And then what is the actual definition of potential energy? You know, they were actually infinitely separated, these charges. Look at this, infinitely separated. Where is the boundary? Where are the boundaries? The boundaries are not coinciding, right? The boundaries are actually far apart. That means they are infinitely separated. And then you're pushing them together, right? Closer, 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 such that their fields are merging. Fields are interacting now. So I could define it this way. Work done to assemble the charges to their present separation from their infinite separation. So repeat after me, please. Work done to assemble the charges to their present separation from their infinite separation. This is called potential energy of the system. Did you understand? I'm asking everyone, tell me please. All right, so I'll give you the question now. Look at this. I have a potential difference here. Potential difference. It's a very important question, many times asked. This is having positive charges all around, all over, and this one is having negative charges. So that creates a potential here, right? What happens if a charged particle enters this? Just imagine an electron. If an electron enters this, the electron will be attracted towards positive plate. Am I correct? Correct? Yes. Okay. So just imagine we have a potential well. This is called potential well. You're just like you're jumping into a well. What happens? Gravity is pulling you down. Similar way, this plate is pulling it towards it. Right. So just imagine you're jumping into a well. You're falling down. Why? Because gravity is pulling you down. Right? Similar way, when the electron jumps into the well, potential well, electron is being pulled towards positive plate because electron has negative charge and this is positive plate. Anyway, it acquires a kinetic energy. What does work energy theorem says? Work energy theorem from first year classes? Work energy theorem? Work done is equal to energy. Work done is equal to energy. Work energy theorem. Work done by the potential. For example, just imagine a truck. This is a truck hitting a car, right? What will happen to the car? When the truck hits the stationary car, the truck imparts a kinetic energy to the car. The car flies off. Or just imagine you're standing in the road like this. All of a sudden a truck hits you. You're flying off. Why? Because the truck is imparting kinetic energy to you, right? So work done by the truck is your kinetic energy now. Similar way, here work energy theorem says that work done by the potential is kinetic energy. So let us put kinetic energy. Kinetic energy is half mv square. What is work done? Work done per charge was defined as potential. This is the very first equation you learn in this chapter, right? Work done per charge, cross multiply. Do you remember this equation? Work done to bring a +1 Coulomb from infinity up to the point. Yes, yes. All right, thank you. So work done per charge is V. Cross multiply, you got Q times V. So Q times V. Remember, this V is potential. That is why I'm using capital letter V for it. While this V is velocity. QV is equal to half mv square. The numerical is to find velocity. How do you find velocity? V square will be equal to 2 comes to the left side. 2QV by m comes to denominator. So V will be what? Root of 2QV divided by m. Trust me, this is very, 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 very important. Now, what is the question that they ask? I'll tell you. If this question comes even in magnetic effects of current, similar question, I'll tell you. Repeating one more time, we have a potential well. Potential well means one plate is positive, the other plate is negative. And an electron jumps into this well. What happens? Electron is pulled towards the positive plate. Why? Electron is negative. Negative is repelled by negative, attracted by positive. So, electron will have a movement to the left. And then it gets a kinetic energy. Kinetic energy is half mv square. Who gave this kinetic energy? Work done by the potential. Work done by the potential is Q times V. Q times V is equal to half mv square. So V square will be equal to 2QV over m. V will be root of 2QV by m. I'll tell you what kind of question is being asked from this. I'll write down 4 particles. Look at this. These are the frequently asked questions. Okay. 1H1, 1H2, 1H3, 2He4. What are these? What are these actually? 1H1 is what? 1H1. 1H1 is hydrogen. 1H2 is deuterium, hydrogen isotope. 1H3 is tritium, hydrogen's another isotope. And this is helium. And if you take the nuclei of these, hydrogen's nucleus is what? Hydrogen atom's nucleus. It's got only one proton, no neutron. So hydrogen's nucleus is called what? Hydrogen's nucleus is called proton. Hydrogen's nucleus, 1H1 is called proton. Hydrogen's nucleus. 1H2 is called deuteron. Deuteron. And 1H3 is called a triton. Triton. And then 2He4 is called alpha particle. Alpha particle. Okay, that is removed from the syllabus now, but you may even have questions. You may have even questions from that part as well, right? I'll repeat one more time. There are 4 particles that they can ask. Number 1, never ever forget this. 1H1. 1H1 is actually hydrogen, but we are talking about nucleus. Hydrogen's nucleus is what? In the nucleus of hydrogen, there is only one proton. So it is called proton. 1H1 is proton. 1H2 is what? Deuterium's nucleus. Deuterium's nucleus is called deuteron. Then this is tritium, another isotope. Tritium's nucleus is called triton. And then helium nucleus is called alpha particle. And they'll ask you what question? I'll tell you. They'll ask you to find the velocities, ratio velocities of any of these particles. For example, one question I'll give you. Find the ratio. The question, previous question, find the ratio of proton and alpha particle. Proton and alpha particle. Okay, velocities of proton and alpha particle. Find the ratio, velocity of proton and velocity of alpha. If they enter a potential, velocity of proton and velocity of alpha, if they enter a potential, how do you find? I can use this equation. Proton. How do we write for proton? I'm writing for proton first. Proton, velocity of proton. 2. Proton's charge is E. V is potential difference is V itself. Proton's mass is M. And what is alpha? What is that for alpha? V alpha is, tell me Manazir, root of 2 into. What is the charge for, tell me Aslaha, what is the charge for Q? A charge for alpha particle? This is the charge number. This is the mass number. This is charge number. This is mass number. Charge number, mass number, charge number, mass number. Charge number is number of protons. Yeah, that's right. That's right, Adya. Right. So for alpha particle, I should write 2E because charge of alpha particle is 2 times E. Into potential difference is same because both enter the same potential. What about mass? Look at the mass number. Alpha particle has 4 nucleons, 4 masses. So that has to be 4m. Then I can take the ratio. They are asking you to find the ratio Vp to V alpha. How do we take? 2 cut, E cut, V cut, M cut. What do we get? On the numerator, nothing. So it is 1. On the denominator, it is root of 2 by 4. It is 1 by 2. So take the reciprocal. The ratio is root 2 is to 1. This is a very, very, very important question. Root 2 is to 1. They might ask you different questions. They might ask you proton and neutron, proton and triton, proton and alpha, then deuteron and triton, deuteron and alpha, then triton and alpha. There can be 6 different questions based on this. Okay. So they'll give you any of these 4 particles, nothing other than these. Anyway, you have to learn these particles because this comes too many times in first book, even in magnetic effects of current, then some other parts. I'll come back to that later anyway. What are the particles? Oh, so I'll quickly repeat whatever we learned in this part. This is what I told you: a charged particle like an electron, a proton, deuteron, alpha particle, or whatever you have. It has to be a charged particle, and the particle enters an electric field, electric potential. Okay. So what happens then? Somebody is giving it energy. Who is giving it energy? Electric potential is giving it energy. So work done is converting to energy. Work done is how much? It is Q times V. Work done is Q times V. Work done by charge, that is the definition of potential. So Q times V is equal to half mv square. Remember, this V is potential difference. This V is velocity. So you cross multiply V square is equal to 2QV over M. V is equal to root of 2QV over M. But this V and this V are different. This V is velocity. You're calculating velocity. The question will be to find out the ratio of velocities of which all particles. They might give you proton and neutron. Question number 2, proton and triton. Question number 3, proton and alpha particle. Question number 4, deuteron and triton. Question number 5, deuteron and alpha particle. Question number 6, triton and alpha particle. There can be different questions. So, and you have to identify the particles here. Proton, 1H1 is actually proton, hydrogen's nucleus. Then 1H2 is deuteron, deuterium's nucleus. 1s3 is triton, tritium's nucleus. 2He4 is alpha particle, helium nucleus. And this is atomic number, which is also the number of protons, charge number. And this is number of nucleons, protons plus neutrons, mass number. So when you want to put mass, you should take the upper subscript, right? And this has to be taken for what? The charge. Charge has to be put here. Did you understand? So we have to write a couple of notes here. Note number one, just draw the figure. This is a positive potential, positive plate. This is negative plate. Okay. And a particle like a proton or electron. Electron is entering, electron will be pulled towards this plate. What is work done? Work done, W is equal to Q times V. We use this in dual nature of matter and radiation as well. Work done is equal to Q times V. Right. This is the most repeated equation in class 12. Okay. Most repeated equation in class 12. Then kinetic energy. What is kinetic energy? Kinetic energy is equal to half mv square. Then get an equation by connecting these two. What do we get? Half mv square. Half mv square is equal to Q times V, or V square is equal to 2QV over M, or V will be equal to root of 2QV over M. This equation is to be learned by heart. Okay. So write this: proton is 1H1, deuteron is 1H2, triton is 1H3, alpha particle is 2He4, helium nucleus. This is hydrogen nucleus, this is deuterium's nucleus, this is tritium's nucleus, this is helium nucleus. Okay, alpha particle. And once you have written this, tell me when you finish this, then we'll do one question. Okay, thank you. Write a question. Find the ratio of velocities of deuteron and alpha particle. Find the ratio of velocities of deuteron and alpha particle entering a potential. Deuteron and alpha particle. Previous question. Deuteron and alpha particle entering a potential. So do it yourself. First of all, write the equation. V is equal to what? Root of 2QV over M. This is the equation to be used. So I am writing deuteron first. How about deuteron? Deuteron's equation is root of 2 into, for deuteron, I must write deuteron here. This is deuteron, 1h2. What is the charge number? 1 is the charge number, right? So I must write only 1e. Deuteron is only 1e. Into potential is V itself divided by what is mass? Mass is 2 times m. Okay. Then V alpha particle. Alpha particle you can write 2 into, what is alpha particle? I must write alpha particle here, 2He4. Charge number for alpha particle is 2e into V divided by, what is mass number? Mass number is 4m. Mass number is 4m. So V deuteron by V alpha is equal to, you've been asked to find the ratio. Let us cut 2e here, V here, m here. So on the numerator I have root 1 by 2 by. On the denominator 2 and 4 are cut, this is 2. So root 1 by 2. So the ratio is 1:1. 1 by 2 is to 1 by 2 is 1 by 1. Did you understand? Calculate the ratio of velocities of, this is a previous board question. I forgot to include that in the paper. Calculate the ratio of velocities of a proton and alpha particle. I solved it as an example question. Calculate the ratio of a proton and an alpha particle entering a potential. Entering a potential. Try that yourself. Entering a potential. Try it yourself. Tell me when you finish this, okay? I want all of you to do. Write a question. You have to attach these 2 questions to the paper, okay? Somehow. You have to take a printout and write it down on the back side. Otherwise, when you refer later on, you'll miss the class. You'll miss this paper, okay? Excuse me. All right. 3 charged particles. 3 charged. It's a previous board question, and the previous one was also a previous question. So make sure that you write these questions on the back side of this paper, okay? So these are the 2 questions that I missed to include. This one is very, very important. Previous question. It's a previous ITJ question as well. Okay, board examination question. For board examination, the charges were 1, 2, 3, but I'm making it slightly simpler. Okay, right. 3 charges plus 1 coulomb each are placed at the corners of 3 charges plus 1 coulomb each are placed at the corners of an equilateral triangle. 3 charges plus 1 coulomb each are placed at the corners of an equilateral triangle of side 1 meter. Calculate the work done. Calculate the work done. Calculate the work done to assemble them. Calculate the work done to assemble them to the corners of a smaller triangle. Calculate the work done to assemble them to the corners of a smaller triangle. Of side 0.5 meter. Of side 0.5 meter. Repeating the question one more time. 3 charges plus 1 coulomb each are placed at the corners of an equilateral triangle of side 1 meter. Calculate the work done to assemble them. Calculate the work done to assemble them at the corners of a smaller triangle of side 0.5 meter. Did you get the question? Okay, right. So let's do this. How do we do this? First of all, we have a configuration. The system is having a potential energy, right? These are like what? These are the corners of an equilateral triangle, no? So that makes it a system of charges. What is the potential energy? I can call it UI, initial energy of initial configuration. And later on, you're doing some work so as to bring them closer to the corners of a smaller triangle. Now that it has a new energy, this is energy of the final configuration. So I can find the energy of initial configuration. I can find the energy of final configuration. Find the difference. That will be the work done. That's common sense, right? Just imagine, this is a car, no? Car moving with a kinetic energy of 100 joules. Just imagine. A truck hits it, so its kinetic energy increases to 300 joules. Okay. So we have a car moving to the left. It has a kinetic energy of 100 joules. All of a sudden, a truck comes from behind and hits it, so that the kinetic energy changes to 300 joules. What is the work done by the truck here? It's common sense. Work done is actually imparted to the car's kinetic energy, right? So work done by the truck is same as change in kinetic energy. That is what work energy theorem says. Same way, if you have done some work so as to bring them closer, the work done by you must have been converted to its kinetic energy. So how do you find work done? Work done can be written as U final minus U initial. You find the initial kinetic energy, initial energy, potential energy, final potential energy, find the difference, that will give you the value. I'm doing it. What is initial energy? 1 by 4 pi epsilon 0, which is 9 into 10 raised to 9. 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. Let us do one by one. Q1 Q2. 1 into 1 by 1 plus 1 into 1 by 1 plus 1 into 1 by 1. Look at that. 1 into 1 by 1 plus 1 into 1 by 1 plus 1 into 1 by 1. Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. So tell me what you get when you upon solving. This is 9 into 10 power 9. This is 1, 1, 1. 1 plus 1 plus 1 is 3. That makes it 27 into 10 power 9 joule. I got initial for potential energy. I can find final potential energy from here. How do you find UF is equal to? That's again 1 by 4 pi epsilon 0. 9 into 10 power 9. Into Q1 Q2 by R12. 1 into 1 by 2. 0.5 may be better written as 1 by 2, right? 1 into 1 by 2 plus 1 into 1 by 2 plus 1 into 1 by 2. So what do we get? 1 by 2 goes numerator to become 2. This is 2. 2 plus 2 plus 2 is 6. 6 into 9 is 54 into 10 power 9 joules. Now that you got both initial and final kinetic energy, you can put them over here. Tell me 54 into 10 power 9 joules. That is final. Minus initial is 27 into 10 power 9. So that will give you 27 into 10 power 9 joules. Did you understand? I'll repeat one more time. What is the question? We have 3 particles, charged particles, assembled at the corners of an equilateral triangle of side 1 meter. Right. And you are doing an external agent is doing a work so as to bring them closer to the vertices of a smaller triangle, right? Of side 0.5, 0.5, 0.5. This was all 1, 1, 1. And then what is the question? Work done to find, work done to, work done to assemble to the corners of the small triangle. What is the work done? Work done in the process is the change in its energy. Initial energy. This is Uy 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. That will give you the potential energy of the initial configuration. 1 by 4 pi epsilon 0, 9 into 10 raised to 9. 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. 1 into 1 by 1 plus 1 into 1 by 1 plus 1 into 1 by 1. So that will make it 27 to the power 19 joules, 9 joules. Later on, when you make it a smaller triangle, work done is 9 energy is 9 into 9 into 1 into 1 by 2. The distance is 1 by 2 now. 1 into 1 by 1 by 2. 1 into 1 by 1 by 2. 2 goes numerator, 2 goes numerator, 2 goes numerator. 2 plus 2 plus 2, 6. 6 into 9, 54 into 10 power 9 joules. Having obtained initial and final energies, I should move on to find the work done. Work done is final energy minus initial energy. That is 54 into 10 power 9 minus 27 into 10 power 9. That makes it 27 into 10 power 9 joules. Did you understand? Everyone? Okay, let's take the paper now. Electric potential, full revision paper. Right. We did till question number, continuously till question number 11. 11, 1 till 11 we did, right? Question number 11 we did. 11 also we did, I think. 11 we did. Yep. Yeah, that's right. Aisha, we did 11, right? Okay. Then 12th one I'll come back and do. That's an important question. 13 13 I'll do now. 14 we did. 15. 16 we did. 17. Okay, I need to tell you one more thing, then I'll come back and do questions. Okay, because all right, see this. Okay, so what is the definition of potential? Definition of potential is W divided by Q. All right, so I have a two particle system. This is Q1, this is Q2. What is the equation for potential energy of the system? Potential energy of the system, we learned this. The potential energy is given by 1 by 4 pi epsilon 0 into Q1 Q2 divided by R. Okay, but this is when it is not placed in an external field. But remember, if it is placed in an already existing field, I must write three terms. This is potential energy between these two part components, right? And then there is one work to be done in bringing Q1 over here. What is the work done? That is Q1 into V. What is the work done for second one? Q2 into V. So if the system is placed in an external electric field, that's a previous question, external electric field. If they specifically say the potential energy of two particle system in an external field, if you see this external field, you must write what? The total potential energy as K Q1 Q2 divided by R plus Q1V plus Q2V. This is an important point again. It's a 2-mark question. That's very, very important. It's there in the textbook as well. I'm repeating. I know you have confusions here. Don't worry. I'll clear them out. Right. What is the potential energy you learn? For a two particle system, potential energy is 1 by 4 pi epsilon 0 Q1 Q2 by R. 3 particle system 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. Right. And those are the equations for two particle and three particle systems. So I'm coming back to two particle system again. Two particle system again. Two particle. Okay. But this time in an external electric field. Okay. In the previous case when we did, that was not in an external field. Understood? But here already, look at this. Already there is an electric field. Into this, charge Q1 is coming. Charge Q1 is coming. So if charge Q1 is coming, work is to be done. What is the work done? Q1 into V. Work done is Q1 into V. Now into this field, Q2 is coming. So what is the work done? That is Q2 into V. Then there is potential energy between these two. That is 1 by 4 pi epsilon 0 Q1 Q2 by R. So what is the total work done then? Q1V for Q1, Q2V for Q2, and for them together it is KQ1 Q2 by R. Total energy is KQ1 Q2 by R plus Q1V plus Q2V. Did you understand? See this. So we learned what? We learned potential energy of two particle system. Potential energy of two particle system is what? 1 by 4 pi epsilon 0 Q1 Q2 over R. For three particle system 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13. We learned those equations. But that is to be, those equations are to be used in the absence of an external field. But if there is already an external field existing, things will be different. I'll tell you. Look at this. This is an external field. Now, into this, Q1 is coming first. What is the work done? Potential's definition is what? W by Q. So, what is the work done then? Q times V. So, in order to bring Q1 into the field, work done 1. That is Q1 into V. Then what? Into this field, you are bringing Q2. Q2. What is the work done for that? Work done for that is Q2 times V. Q2 times V. And then field list, when Q2 is brought in, Q1 is already there. So between them, there is a potential energy. What is that? That I can call W3. That is K into 1 by 4 pi epsilon 0 K Q1 Q2 by R. Because the distance between them is R. So what is the total work done then? Q1V plus Q2V plus K Q1 Q2 over R. This is the equation for potential energy of a two particle system in an external field. They will specifically ask, it's a repeated question, in an external electric field. If external electric field is not mentioned, you can stop with the first, last term. You can write only last term. Did you understand this now? 15th question, second part. Deduce the expression for potential energy of a system of 2 point charges Q1 and Q2 brought from infinity to the points R1 and R2 respectively in presence of external field. That 15th question is a 3-mark question. First part carries 1 mark, second part has 2 marks. Did you understand? First part we did in the last session, second part, it's all about second part now. Read second part once again. Deduce the expression for potential energy of a system of 2 point charges Q1 and Q2 brought from infinity to the points R1 and R2 respectively in presence of external electric field. Okay, so you are bringing them. This is the external electric field. You are bringing Q1 first, then you are bringing Q2, right? So how do you write the potential energy? First one, W1 is Q1V, W2 is Q2V. So W3, between them, it is KQ1 Q2 divided by R. So you have to add them up. That will give you Q1V plus Q2V plus KQ1 Q2 divided by R. Did you understand what we did now? Before moving to 12th question, I'll tell you something. Look at this. This is a particle, this is a sphere. What is the potential on the surface of the sphere? Potential on the surface of the sphere, potential outside. This is not explicitly given in textbook, but you can have questions. You may have questions on this. Okay, it's a sphere. Sphere, when I say sphere, it is a conducting sphere, conducting spherical shell, whatever you call. It's a spherical shell or a solid sphere. Okay, what is the difference between spherical shell and solid sphere? Shell means it is hollow inside, like a football, right? Solid sphere means it's all solid inside. There is matter inside, like the ball used in shot put. Understood? Okay, so it can be solid or hollow. That's my point. Solid conducting sphere or hollow conducting sphere. Anyway, outside potential is given by KQ over R. Surface potential is given by KQ over capital letter R, where capital letter R is the radius. Small letter r is the distance to the point. V inside is same as V surface, which is KQ divided by R. This is capital letter R. Okay, so I'm repeating one more time. What are we looking at now? Potential due to a sphere. Potential due to a sphere. When I say sphere, I'll write it here. Potential due to a sphere. Sphere means spherical shell, conducting sphere or conducting spherical shell or solid sphere. I told you the difference between shell and solid sphere. Shell means what? Shell means it's hollow inside. Shell is hollow inside. Okay, shell is like a football. Solid sphere means it's full of matter. Okay, it's full of matter. Okay, anyway, for a sphere, the derivation is not there in your syllabus. Even this is not explicitly given, like I said, but you will have questions, numericals. I'll tell you which all questions. You don't have to learn anything else. Trust me on that. Okay, so spherical shell. This is spherical shell. What is the potential outside? Potential at a point P at a distance R, outside point. Potential outside is 1 by 4 pi epsilon 0 Q over R. Potential on the surface is how much? 1 by 4 pi epsilon 0 into Q over capital letter R. Potential inside is how much? That is also same as surface. Remember, field was 0 inside. If you remember, field was 0 inside, but that is not there in syllabus anymore. This time they have removed it. But potential they may ask. And the graph would look like this. This graph is one question, important question. V against R graph. Potential against distance graph. Look at this. Inside and surface, potential is the same, no? That is why the graph is a horizontal line. But outside, it is decreasing exponentially. Understood? That is question number 1. Question number 1. Did you understand? Question number 2 is, I'll give you. Now, question number 12. A charge plus Q is placed on a large spherical conducting shell of radius R. A charge plus Q is placed on this. Its radius is given. Its radius is capital letter R. Okay. And then another small conducting sphere of radius small letter R carrying a charge Q is introduced inside. Another small sphere of charge Q is kept inside. Okay, with radius equal to small letter r. Then inside the large shell and is placed at the center. Find the potential difference between 2 points. One lying on the sphere. Potential difference between this point A and one lying on the shell. Part B, how would the charge between the two flow if they are connected by a conducting wire? We'll see the second part later. For the moment, we'll focus on the first part. Read the question once again, draw the figure. I'll tell you how to interpret the question. So read the question again, one more time, please. A charge plus Q, a charge plus capital Q is placed on a large spherical conducting shell of radius capital letter R. So large spherical shell has a radius capital letter R, charge plus Q is placed on it. And then what? Another small conducting sphere of charge Q, small conducting sphere of radius R, radius small letter R, carrying a charge Q is introduced inside. So large sphere has a charge plus capital Q, its radius is capital letter R. Then a small sphere is introduced inside whose charge is small letter Q and its radius is small letter R. Okay. And what is the question? Find the potential difference between 2 points, one lying on the sphere A and the other on the potential. Okay, so what is the question? I have to find the potential here. I have to find the potential here. Okay, on a first look, it may look very simple, but it is actually a complex one. I'll tell you why. What is the potential? Okay, I can write the potentials one by one. Okay, I'm writing potential on B first. Potential at B. B is where? B is on the inner sphere, right? I'm taking 2 points. One on the inner sphere, second one on the outer shell. So inner sphere, I'm taking the point B. I'm going to find the potential at B. It is what? It is a sphere. What is the potential on the surface of the sphere? Do you remember? We learned this. K into its charge divided by its radius. I'm not done yet. This point is what? This point is actually an inside point for the outer shell. Correct? Inside point. This point is, yeah, that's right. This point is actually what? That point is surface point for the sphere and inside point for the shell. Right? So the potential at this point has 2 components. Which are them? Tell me. One is by the sphere, second one by the shell. So I must write VB as V due to sphere should be there plus V due to shell should be there. Okay. There are 2 because this point has what? Potential due to the inner sphere, potential due to the outer shell. Outer one is called shell, inner one is called sphere. So let us write what is potential due to sphere? K into sphere, sphere is surface point. Surface potential is what? K into its charge divided by its radius. But as far as the shell is concerned, it's an inside point. So how do we take for inside point? K into its charge divided by its radius, because for inside point, it is same as surface potential. Did you understand this? Till this much? No. Shell contains only one charge. Shell has plus capital Q. The sphere has small q. I'm repeating one more time. Potential at B. Where is this point B? B is on the sphere, inner sphere, no? So I have to find the potential at B. Potential at B is due to 2 components. Which are they? One due to the sphere itself, another one due to the shell. Because in the vicinity, there are 2 configurations which can give potential. No, the shell can give a potential because it's got charge on it. Sphere can give a potential because it's got charge on it. Correct. Both the sphere and shell will provide potentials. I am just writing them down. That's it. What about the potential at this point then? Potential due to sphere. What is that? It's K into its charge, small letter Q, divided by its radius, small letter R. Then what about potential due to shell? Shell, K into its charge. Its charge is capital letter Q, divided by its radius, capital letter R. Did you understand this now? Now, second one, I'm going to find out potential at A. What is potential at A? Potential at A also has 2 contributions, V sphere plus V shell. Potential at A. A is what? A is surface point for this, right? Surface point. But for inner sphere, it is what? Inner sphere. Inner sphere, it is actually an outside point, no? Outside point. So K into its charge divided by distance to that point. Distance to that point is capital letter R, plus for the shell, it is surface point. So KQ over R. That is equation number 2. Equation number 1. This is VA. I'm repeating one more time. What is the potential at A? Potential at A. Once you have got it, you know it's going to be easy. Initially, it may look complex. So potential at A is what? Potential at A has two components. What are they? One due to the sphere, second one due to the shell. What about the sphere? For the sphere, this point is an outside point, right? It's outside the sphere. Outside the sphere. If it's outside the sphere, how do we take it? Oh, tell me what? Outside the sphere, KQ by distance. Do you remember? So K into its charge, Q divided by distance to the point. Distance to the point is actually what? Capital letter R. So KQ over capital letter R plus due to the shell, how do we take it? Shell. For the shell, A is a surface point. Surface point, K into its charge divided by its radius. These are the potentials. Now I can take VB minus VA. VB minus VA. What do we get? VB minus VA. They are asking you to find the potential difference. When you take the difference, KQ by R getting cancelled. So I take KQ by small letter r minus KQ divided by capital letter R. So if I take KQ common, 1 by R minus 1 by capital letter R. That will be the potential difference. Okay. Did you understand? So we have a spherical shell inside which a sphere is kept. Sphere has a charge of small letter q. Sphere has a radius of small letter r. Shell has a charge of capital letter q. Shell has a radius of capital letter R. I'm finding potentials at B and A. Where is B? On the sphere. Where is A? On the shell. So potential at A will have two components. Potential at B also will have two components. Potential at B, I'm looking at potential at B now. What about B? Potential at B is potential due to sphere plus potential due to shell. What about B? Where is B? For the sphere, it is a surface point. It is on the surface, which means K into its charge, that is Q, divided by its radius, that is R. That is how you take surface potential, KQ by R. Plus, what about that due to shell? For the shell, this point is actually an inside point. It's inside the shell, no? Inside the shell is same as surface. Its surface, right? Its surface. K into its charge divided by its radius, KQ by capital letter R. So I'm done with the first equation. Second equation, similar way, potential at A also has two components, right? A has two components. Which are they? A is what? A is on the surface of the shell and it is outside the sphere. For the sphere, it is an outside point. It's outside sphere, right? Yes, even though it is on the shell, it is outside for the sphere. Correct. So I can write VA as V sphere plus V shell. What about sphere? Due to sphere, it's an outside point. Outside point, how do you take? K into its charge. Sphere's charge is Q divided by distance to that point is what? Distance to that point is capital letter R plus for the shell. Shell, it is a surface point. A is a surface point. How do we take it? K into its charge divided by its radius, KQ by R. You are asked to take the difference between potentials, potential difference, right? KQ by R being equal, they get cancelled. KQ by small letter r minus KQ by capital letter R. So if I take KQ outside, KQ into 1 by R minus 1 by capital letter R. Is that clear now? So let's move to the last part. Second part asks you to do what? If they are connected by wires, how would the charge between the two flow if they are connected by a conducting wire? You're going to connect them by a conducting wire. Okay, connect them by a conducting wire. No, you are connecting the spheres. Read it again. How would the charge between the two flow? How would the charge flow? Charge flows from where to where? You know, you have a bucket of water here. Okay, you got another bucket with a lesser amount of water. You connect them through a pipe. Water flows from where to where? Water flows from where to where? Higher level to lower level. Am I correct? Higher level to lower level, right? Yes. Similar way, charge flows from higher potential to lower potential. Let us see. You know, which radius is smaller? Which radius is smaller? R is smaller, right? Than capital letter R, right? So this denominator is lesser means this value will be greater. So greater minus smaller means what? It's positive. VB minus VA is positive. Look at that. Look at this. You know, R is, see, R is less than capital letter R. Small letter R is smaller radius. Capital letter R is bigger radius. So small letter R is less than capital letter R. That means this value is lesser. This denominator is lesser than this denominator. When denominator is lesser, this fraction is more. This fraction is less. So when you subtract a smaller number from a larger fraction, you get positive, right? You get positive quantity. So right side is a positive quantity. If right side is positive, which should be greater? VB is greater than VA. So B has greater potential. B is at a greater potential. So charge flows from inner sphere to outer shell. Outer shell. I'm repeating that part one more time. Second part of the question asks you to identify the direction of charge flow. If they are connected by a wire, it is like what? You're taking two buckets of water with different levels of water and then connecting them through a pipe. Water flows from higher level to lower level. Similar way, here charge flows from higher level to lower level, higher potential to lower potential. So it's all about identifying which one is at higher potential. How do we do that? Look at this. R and R. If you compare R and R, no, small letter R is small radius. Capital letter R is big radius. So small letter R is less than capital letter. Where is it? Small letter R is less than capital letter R. That means this denominator is less than this denominator. Which means when denominator is less, fraction will be more. This fraction is more than this fraction. So smaller fraction subtracted from bigger fraction will give you a positive quantity. So VB minus VA is positive. If VB minus VA is positive, VB is greater for sure. VB is greater than VA. Potential at B is greater. Potential at A is lesser. Okay, so charge flows in this direction. Charge flows from inner sphere to outer shell because B is a sphere point on the sphere, A is a point on the shell. Charge actually flows from B to A. Did you understand? Last question, define the term potential energy. Question number 13. Define the term potential energy of a charge Q at a distance R in an external field. What is potential energy of Q? Potential energy of a charge Q. It is the work done. Potential energy of a charge Q. It is the work done in order to move a particle from infinity up to the point in an external field. What is potential energy? It is same. It is actually what? Potential is what? Work done to bring plus 1 coulomb from infinity. This is Q coulomb from infinity up to the point. Okay, in an external field. Read it again. What is the question? I'll read the question one more time. Define the term potential energy, not potential, potential energy of a charge Q at a distance R in an external field. What is potential? Work done to bring plus 1 coulomb from infinity up to the point. Similar way, work done to bring Q coulombs of charge from infinity up to a point in an external field. Did you understand? Repeating one more time, work done to bring a charge Q, not plus 1 coulomb, charge Q from infinity up to a point in an external field. Did you understand?